Okay, so yesterday we left off with talking about quadrilaterals. Okay. Also, we learned another name for them, tetragons. Tetra meaning four, but we'll pretty much stick with the term quadrilateral. Okay, so a few other terms we're going to learn about polygons in general, and then as the chapter goes on, we're going to start to focus specifically on four-sided quadrilaterals. Okay, so what does it mean if a polygon is equilateral? Well, we know what it means if it's a triangle. It means equilateral, all the sides are the same. It's the same thing here. So if a polygon is equilateral, that means all sides are congruent. Okay? If a polygon is equiangular, well, think back to what it means about a triangle. Triangle is equiangular, all the angles are equal. In a polygon, it's the same thing. All of its interior angles are congruent. It's just there's more of them. Okay, so in a square, for example, that would be considered equilateral, polygon. All the sides are the same. Also, we could say all its angles are the same. If all the sides are the same, does that mean all the angles will always be the same?
No.
No. Think of, I don't know if I can draw it perfectly on here, but if I can find a rhombus, that's not a rhombus. Yeah, it's not letting me, oh, now it's got it. Okay. There's a rhombus. All the sides are the same there, so that would be considered an equilateral polygon, but I hope you can tell, certainly it's not equiangular. Two of the angles are much bigger than the other two.
A trapezoid would be a two, right?
A trapezoid? If you were to draw a trapezoid, well, it wouldn't be...
It wouldn't be equilateral.
No.
No. Because if you draw it right, like...
So in a trapezoid, your bases,
longer than average.
they're going to be different lengths. Okay, they're going to be different lengths. So trapezoid's not going to be equilateral, and not equiangular either. So trapezoid really wouldn't fit that. But then if we combine both of those together, if something's equilateral and equiangular, then we call it regular. Okay, so here's an example of a, let's see if I got a regular, okay, yep. That's a regular shape, regular polygon. It's equilateral and equiangular. Okay. There's another one. That's a octagon. It's equilateral and equiangular. So that's called a regular octagon. All angles the same, all sides the same. Okay. Any of these shapes that you see down here, numbered 3 through 12, and even higher, they're all regular polygons. Equilateral and equiangular.
Can't you have an octagon that is not a regular octagon?
Yeah, oh yeah. Yep. Any 8-sided, just draw something that has 8 segments. So 1, 2, 3, 4, 5, 6, 7, 8. There's an example of an octagon that's not regular, because some segments look a little shorter, some look a little longer. Yeah. That's specifically a concave octagon as well. Good question. How about that shape? Is that regular or not? What do you think?
It's not regular.
Nope. Why not?
Because two of the angles are the same. And
It's definitely equilateral. All the sides are the same. But is it equiangular? No. The top 2 angles are the same. The horizontal left and right are the same, but they're not all the same. So nope, that's not regular. How about that one? What do you think? Is that a regular? In this case, that's a pentagon. But is it regular, Marquise?
yes.
Yeah. All the sides are the same. They're all marked congruent. All the angles are marked congruent. We're good. That's a regular pentagon. Okay. It's also convex. Sorry, convex. Okay. I guess you could ask yourself, would it be possible to have a regular shape that's concave?
I'm thinking
Okay.
yes.
I have to think about that. I think I could make something that's concave and maybe all the sides come out the same. But I don't know if I can make all the angles come out the same. Well, you have to think about that a little bit.
I'm thinking yes.
Yeah, we could think about it. How about that one, Pac-Man?
No.
Kind of. Is that a regular shape? Regular polygon? What do you think, Luke?
No.
No. All the sides are marked the same, but what's not the same?
The angles.
Yeah, the angles. Okay, so no. Okay, it's definitely concave. You can count up the number of sides and figure out what kind of shape it is based on that, but it's not regular. Okay, so we'll finish up this page, then I'll put up the homework for this section, and then we'll do section 6 too. Okay, so what is a diagonal? Okay, a diagonal is basically it's a segment that connects two vertices that aren't consecutive. So I drew a triangle. Do you have diagonals in a triangle? No. I don't care what two vertices you pick in a triangle, they're always next to each other. Pick any two you want. Pick the top one and the bottom left, pick the top one and the bottom right, or pick the bottom left and the bottom right one. They're always going to be next to each other. You've got to have more than 3 sides to have diagonals. And what, I don't want to get into it too much, but what might be an interesting pattern is the number of sides you have and the number of diagonals. So you can see for a 4-sided shape, how many diagonals do you have? 2. So with a 4-sided shape, you get 2 diagonals. How about for a 5-sided shape? It's a little tough, but try to count them up.
4.
How many?
4.
All right, let's trace over on this sheet. So we got 1, 2, 3, 4, 5. So for a 5-sided shape, you get 5. Just looking at those 2, you probably really can't find a pattern. Let's look at that side. How many sides does that shape have?
It's a hexagon, so 6.
Yep, 6 sides. Let's see how many diagonals. Okay, the easiest way is to try to trace them over in a different color. Okay, so we get 1, we get 2, 3, 4. Let's see, we got 5, 6, 7, 8, 9, and I think I got them all. So that one has 9. So you might guess that, 2 to 5, you went up by 3. 5 to 9, you went up by 4. So the next one, maybe you go up by how many? 5. So maybe if you have 7 sides, you'd have 9 plus 5, or 14 diagonals. Might be a pattern you could look at and try to figure out. And that pattern would come in handy if I said, how many diagonals does a 35-sided shape have? You don't want to try to draw them, because it's probably going to be in the hundreds, maybe it even's in the thousands, well, probably hundreds. Okay? But if you can find a pattern, it would make that easier to figure out. I'd say if we had one more row of data here, we could probably come up with a pattern pretty confidently. With 3 rows, I'm not 100% sure yet.
You should just look it up.
Could you look it up?
Yeah.
Well, on a test, no. You'd have to figure out the pattern yourself on the test, if I asked you.
So is that a hint?
I don't know, could be. But I tried to give you a kind of a little bit of a lead on what the pattern might be. So if you take a quadrilateral, any quadrilateral, and you can basically draw in a diagonal, and that makes it into 2 triangles. What do the angles in a triangle add up to? All the interior angles. Yeah, 180. Okay. So what do you think the angles inside a quadrilateral will add up to? It's going to add up to 360. So if a quadrilateral is basically two triangles, okay, draw any kind of quadrilateral you want. Draw in a diagonal. Okay, you just made two triangles. Each triangle adds up to 180 degrees. So quadrilateral adds up to 360. Interior angles. And there is a very well-known pattern for this. Okay? So if I said to you, what do all the angles in a pentagon add up to? Right? Or a hexagon, or an octagon. Right? It keeps going up higher and higher, and there's a pattern to it.
It always equals 360.
What's that?
It always equals 360 if it's a polygon.
If it's a quadrilateral, yes. But a triangle is different, pentagon's different, octagon's different. Depending on the number of sides, it's always different. But there is a pattern for that. Okay, for now, we'll just stick with that. Or actually, no, let me show you the pattern. So for a quadrilateral, that's actually a theorem. The sum of the measures of the interior angles is 360 degrees. Okay. So now you can use that fact, just like you did with triangles, to say solve for x. Okay, if you don't know what a variable is, but at least you know what all the angles have to add up to, that'll help you. Great, so let's look at one example here. So in this example, they want you to find angle Q and angle R. Okay, they tell me angle T and angle S. Now, if this was a parallelogram or some other kind of special quadrilateral, there's all kinds of other properties we could use. But this is just a generic quadrilateral. Okay, we don't know anything about it other than the angles add to 360. Anybody have a thought or a guess or an equation I could set up that would help me solve for x first, and then once we find x, we can find angle Q and R. Yeah, Ian?
50 plus 3x equals 360.
Okay. So what he did is he added up all those angles. I'll just do it in 2 steps. Angle T plus S plus angle Q plus angle R. What do they all add up to?
150 plus 3x.
So what do all those angles add up to, though? Yeah, add up to 360. Okay, T, S, R, and Q. Add them all together, and you're going to get 360. Okay, so he added 80 and 70. He added x and 2x. And if you jump right to that for your first equation, that's fine. Okay, James, what would my next step be?
So it'll be subtract 150.
Yep, subtract 150. 150 minus 150, that cancels. And Jacob, what's 360 minus 150?
200.
Yep, 210. Last step, divide by 3. So x would be, how about Nick? 70. Good. So now just make sure you answer the question they asked. They didn't ask what x was. They asked what Q and R were. So if x is 70, how big is angle Q? 70. How about angle R?
140.
140.
It's obviously not drawn to scale.
No. No, make sure you never, you can't go by the diagram because it might not be drawn to scale. Okay, any question on that? Same kind of idea, we've done this with triangles. Now just keep in mind in a quadrilateral it adds up to 360, not 180. Basically every angle you add keeps going up by 180, or every side you add. So like for a pentagon, take 360, add another 180, it's 540. For a hexagon, the angles add up to another 180 more. Okay. the way I remember it is how many triangles can you kind of break that picture up into? Quadrilateral, you break it up into 2. So it's 180 times 2. Pentagon, no matter how you draw it kind of like a home plate or something, you could separate it into 3 triangles. 1, 2, 3. 180, 180, 180. So the angles in a pentagon add up to 540. And you could keep going with other shapes. Okay. Any questions on that one? All right. All right. So let me put up, this is the first part from that section. Okay, it's pretty straightforward. Most of it is identifying, is it regular, is it equilateral, equiangular? It's a lot of quick questions. So it's page 326, numbers 23 to 31 all, and 37 to 45 odd. What I'll do is I'll copy that, and if I remember, I'll try to paste it at the end so it's with the other one as well. Okay, and section 6.2, we're going to start to talk specifically about parallelograms. So parallelograms are a special type of quadrilateral. And what makes something a parallelogram is it has 2 pairs of parallel sides. Okay, both pairs of sides have to be parallel. Okay, so remember how we indicate that sides are parallel? We use those in your book. Sometimes they're colored red triangles, or they could just be those little arrows. So this indicates that side QR and PS are parallel. PQ and SR are also parallel. And you name it, just like we talked about naming a polygon. Pick a vertice, and then name all the letters, either clockwise or counterclockwise consecutively. So you could go PQRS, RSPQ, QPSR. Any of those names are fine. You just can't jump across on a diagonal. Okay. All right, so there's our parallelogram. Okay, we're going to go over some different theorems about parallelograms. Okay, in general, there are a lot of theorems in chapter 6. Okay, there's a lot. We're going to try to break up the theorems by shape. Okay, so we're going to start with the ones about parallelograms. You might want to leave some room in your notes to write other theorems about quadrilaterals if you want them all in the same spot. If not, that's fine too. But I'm just letting you know there will be a lot of theorems about quadrilaterals. Okay, here's one theorem. Okay, if a quadrilateral is a parallelogram, then the opposite sides are congruent. Okay, that is not part of the definition. The definition of a parallelogram just says that the opposite sides are parallel. But if that happens, a theorem says that the opposite sides are also congruent. Okay, so all these theorems are going to be on page 330. So if you want to take them down or you just want to look in your book for them, that's fine too. Okay, here's a theorem about angles. Okay, it says if a quadrilateral is a parallelogram, then the opposite angles are congruent. Okay, we're going to try to prove a couple of these. And our proof is going to be based on making some triangles. So if a quadrilateral is a parallelogram, then the opposite angles are congruent. So for each theorem, I wrote it in words, and then I got a diagram of the theorem down below. Okay, here's another one, Theorem 3. It says, if a quadrilateral is a parallelogram, then the consecutive angles are supplementary. Consecutive angles are supplementary. What does that mean? Consecutive is any two angles that are next to each other. If you add them up, they're going to add to 180 degrees. Okay, kind of another special property of parallelograms. Okay, and the fourth special property, it says that if a quadrilateral is a parallelogram, then the diagonals bisect each other. What does that mean? The diagonals cut each other exactly in half. So that segment and that segment are the same. And the two segments with the double tick marks are the same. Now, since a rectangle is a parallelogram, we haven't learned that yet, but I'm telling you that. A rectangle is a parallelogram. Every property I just said here applies to rectangles. Every property I just said here applies to squares. It also applies to rhombuses. Each one of those shapes I just said has even more of its own specific properties. Okay? But right now, I'm giving you kind of some general properties that apply to all parallelograms. Squares, rectangles, rhombuses, and just a parallelogram. Okay, so again, those are all on page 330. You might guess this fourth property. This would come in handy when you have to draw triangles and prove that triangles are congruent. Okay, because you've got some sides that already match up. You got vertical angles in here. So we can do a lot with congruent triangles. It'd be very easy to prove that this top triangle and bottom triangle are congruent by side angle side. And the same thing with the left triangle and the right triangle. They're also congruent by side angle side.
When you cut them in half, exactly in half, isn't that also the bottom and the top meaning are the same?
Well, that was another theorem, so that if a quadrilateral is a parallelogram, opposite sides are congruent. So it is true that this side and that side are the same, but now we're combining a couple theorems together. And this side.
You can do that, right?
Oh yeah, yep. And now those triangles are congruent by side, side, side. The top and the bottom, and the left and the right. Yep. So there's all kinds of things that match up here. We could also get into angles. Yeah, opposite angles are congruent. Tons of stuff. Any questions on those four theorems? All right, so before we do any proofs, if we can get to some proofs, let's just try some calculations. Okay, I've given you a shape here that's a parallelogram. You know it's a parallelogram because the sides are marked parallel, both pairs of opposite sides. They want you to find JH. How long would JH be? And then I'm going to ask you which theorem tells you that. Marquise?
5.
Yep. It'd be 5 units. And which theorem tells you that?
First one.
Yep. In a parallelogram, opposite sides are congruent. Well, you know the top side's 5, so the bottom side's 5. Good. Let's find the length of segment JK. How long is segment JK? Then I'm also going to ask what theorem.
3.
Yep, it's 3.
I just have a question.
Can you tell me your theorem first?
I believe it's probably the last one.
Yeah. Diagonals bisect each other. That means each part of the diagonal is cut. It's cut into 2 equal pieces.
Do these only work with regular polygons?
These only work with parallelograms.
Parallelograms?
Yeah. So
Only-
parallelograms includes your basic parallelogram, your square, your rectangle, and your rhombus. Yep.
But they don't work, like,
Just don't work with trapezoids. Nope.
they have to be regular. No.
They have to be parallelograms.
Parallelogram.
Yep. Parallelograms don't have to be regular. These parallelograms, all the angles are not the same and all the sides aren't the same. The only quadrilateral that is a regular parallelogram would be a square. Both pairs of opposite sides are parallel. All sides are the same in a square. All angles are the same in a square. But that'd be the only one. Okay, any other questions on that one?
Wait, so if you draw a shape like that, that's a parallelogram.
As long as both pairs of opposite sides are parallel. You have to have two pairs of parallel sides. So that's why I said rectangle falls under that, rhombus falls under that, square falls under that. Okay, so here's another parallelogram. This time I'm looking at a couple angles. What would the measure of angle R be? Well, Olivia?
70?
Yeah, it would be 70. How do you know that?
Second theorem?
Yeah, the one where the opposite angles are congruent. So P and R are the same. Q and S are also the same. In fact, let's find Q. What would angle Q be there? Another theorem we haven't used yet that will help you with this one. Yep. It'd be 110. In a parallelogram, consecutive angles are supplementary. So Q is 110. What does that mean S is? 110. If I asked about it, yep, I did. Now, there's a couple reasons why you could say S is 110. You could say, well, since I know Q and S is opposite Q, opposite angles are congruent. Or you could say, since I know P, P and S have to be supplementary. Either reason. All right, so S is also 110. And now if I asked you for angle R, no, we already did R. Never mind, that's all. Okay. Any questions on that? Okay, you could have also used the fact that all the angles in a quadrilateral have to add up to 360. Right? If you already knew P, R, and Q, add all those up, and whatever's left over has to add up to 360. Okay, so there's all kinds of ways to figure out sides and angles in quadrilaterals, and especially parallelograms. All right. So here's a parallelogram. I didn't have to write this statement up above. I've already labeled it. Okay. But so just in case you don't see it written that it's a parallelogram, just look for the marks. Okay. They're asking to find the value of x. Okay. Anybody just tell me, what do you know about angle P and angle S? There's a special relationship there. Yeah.
There's supplementary.
They're supplementary. What does that mean?
They both end up to 180.
Right. They add up to 180. Angle P and angle S have to add up to 180. So if I take angle P plus angle S, they total 180. So subtract 120 from each side. That's going to leave you with 60. So what is x here? Yeah, 20. Now go back, read the directions, and see, did they want you to find x or did they want you to find the angle? They said find x, so we're done. If they wanted the angle for P, now I'd plug 20 back in. 3 times 20 is 60, but you would have known that it's 60 anyway, because 120 in that had to be supplementary. So you could have figured out what that angle was without going through the work to find x, but they did want x. Any question on that? X is 20. So not too bad. Okay, let's look at this one. Let's see, a couple seconds last one. So we've got these shapes drawn, and it says ABCD is a parallelogram. Okay. I didn't label it with the marks, but I wrote it down. ABCD, in fact, if it helps, we can just kind of outline it. That's a parallelogram. And it also says AEFG is a parallelogram. Okay, so AEFG, so this one. Okay, what they want us to do is prove angles 1 and 3 are this congruent. Okay, we want to prove angles 1 and 3 congruent. Now, this can actually be done in very few steps. I think 3 steps if you do it correctly, and 3 steps includes the given. All right, so let's start out with that. Okay. So there's your given. ABCD is a parallelogram. AEFG is a parallelogram. You can just use that symbol. You don't have to write out parallelogram, since we're going to write that word so much. Okay, so there's your given. Okay, let's go back up, see if we can figure out step 2.
I've seen another way of doing it, but it's multiple steps.
Anybody tell me anything about the angles that are labeled there? Like say angles 1 and angle 2, or angle 2 and angle 3. How do you know angle 1 and 2 are the same? Yeah, it's that theorem that says opposite angles are congruent. So angle 1 and angle 2 are congruent.
You could probably combine that and say 2 and 3 are congruent.
Yeah, we could also say 2 and 3 are congruent, same reason. Look in the green parallelogram, 2 and 3 are opposite angles. Okay?
And then by the, what is,
Yep, let's just write our reason first. So our reason will be opposite angles of a parallelogram are congruent. You don't have to write or memorize theorem numbers. So opposite angles in a parallelogram are congruent. Any question on that? So 1 matches 2, 2 matches 3. Now what can you say? If angle 1 is congruent to angle 2, and angle...
Substitution.
Okay, you could use substitution and say what?
Angle 1 is congruent to angle 3.
Yep, you could use substitution. What other property could you use we've used before? This one's come up a lot. Yeah, you could say the transitive property. 1 is congruent to 2, 2 is congruent to 3, so 1 is congruent to 3. Okay. When you write substitution, make sure you know I know it's substitution and not subtraction. So if you just put SUB period, I don't know if you mean subtraction property of equality or substitution. So just write out substitution. And that's it. That's the whole proof. Okay, we didn't even have to break these down into triangles. We just had to use properties of parallelograms. Okay, any question on that one? All right. So the last one we're going to try to do is a proof of theorem 6.2. Okay, 6.2, put up the diagram, has to do with proving this. Okay, I'm telling you that the shape there is a parallelogram. So by definition, all you know is that opposite sides are parallel. I also drew in a diagonal. I want you to prove that opposite sides are congruent. Prove that AB and CD are congruent, and AD and BC are congruent. Now, maybe we'll just do half of this, because I don't think we're going to have enough time to do the whole thing. But if you can prove that 2 of the sides are congruent, to prove the other 2 are congruent, it's the same steps again.
You can't use that theorem though, correct?
Yeah, you can't use any theorems we haven't proven. All you can do is use stuff based on triangles, parallel lines cut by transversals, anything like that. Okay, so you do have a lot of parallel lines here, and I did draw in a transversal. So that's going to help us. Let's start with the given. What am I given?
A segment AB and segment DC are parallel.
Okay, and AD and BC are parallel, so that means that the shape is a...
Parallel.
Right, that's what we're given. We're given that the shape is a parallelogram. Okay, so write that down. ABCD is a parallelogram. Given. Okay, now step 2, I kind of already did this for you. In the book, the proof would be done like this. Okay? All they would do is give you the parallelogram, but if you're going to prove this, you've got to add in a line. All right? Adding in a line is going to help me to do some work with triangles. Okay? Why are you allowed to do that? Because between any 2 points, you can always draw a line. That's the reason. So step 2 is to draw that segment in, BD. The reason, to any 2 points, you can draw a line. That's one of the very basic ideas of geometry that we started out with. Kind of like parallel lines not crossing. It's another very basic postulate of geometry. Through any 2 points, there is one line. Okay, step 3. Because this shape is a parallelogram, now we can go into what that means. That means you have parallel sides. So you can't talk about parallel lines and transversals till you say that the lines are parallel. You've told me it's a parallelogram, but you haven't said AB and DC or CD are parallel. Okay, so let's say that. AB is parallel to CD. Okay. And what else do we have? AD and CB. Okay, and the reason for that, that's the definition of a parallelogram. You said it was a parallelogram, now you're going into the definition. Well, let's use this symbol. So when you're writing a proof about a parallelogram, don't ever jump right to saying opposite sides are parallel. Have you told me it's a parallelogram first? If you haven't, you can't say step 3 because you haven't shown me you have a parallelogram. Okay? But we did. We said that in step 1 that we had a parallelogram, so step 3 is fine. Okay, let's look at some of the angles we have there now. Let's look at angle ABD. Anybody tell me what that would be the same as? Based on the parallel lines and that transversal? It'd be the same as something else in the triangle below it. Yeah. CDB. Yeah. Let's write that down. Angle ABD is congruent to angle CDB. And while we're writing that, we can actually look at something else. How about that angle? Angle DBC. Anybody tell me what that one would be the same as? This time you're looking at your parallel lines that are going in the more vertical direction rather than the horizontal. So that's the same as, Luke?
Angle ADB.
Yep, ADB. And the reason, if you don't remember, that's called alternate interior angles theorem, not the converse. Alternate interior angle theorem. Okay, and the last part I'm going to have time to do with you is dB is congruent to dB, so it's reflexive. It's congruent to itself. That's reflexive. Okay. Now, on your own, see if you can figure out why two of these triangles are congruent. You've got some angles matching, you've got some angles matching, you've got a side matching, so maybe angle, side, angle. Okay. Once you prove triangles are congruent, then by CP/CTC, that means the sides also have to match. So this proof is basically done, except for saying the triangles are congruent by angle, side, angle, and then saying CP/CTC. Okay, so there are 2 steps left. If you want to look at it, it's on 332. All right, so the last part of the homework will be on 334, 20 to 36 all, 39, 48, 52, and 56. And if you need the first page again, there it is.